Dear students, today we'll see the functional block diagram of digital communication system. Okay. Now first we have to see the block diagram and then we have to explain each block of that block diagram. So let's start with the today's topic. It is block diagram of digital communication system. Now here students you see the block diagram. Now this is the block diagram of your digital or communication system. Now, initially here you are having something called as source. This is source. Now, this source is information source actually. It can be of two types. It can be a analog information source or discrete information source. If it is analog information source, then it is one which will emit or which will give continuous amplitude signal, like for example, output of your microphone. Okay. And if it is a digital information source, discrete information source, then it is a source that will give a finite set of symbols as possible outputs. Now remember here the word symbols. If it is a discrete source, if this is a digital or discrete source, it will give a set of symbols. Okay, this is very important. Okay. Now that symbols can be anything according to the source which you are going to use. Okay. Now then after that you have a input transducer here. Here you are having input or transducer and it is called as analog to digital converter. Okay, so if the message is analog, then it will be converted into digital. And if the message is a digital, then it will be taken as it is. So at this point, you will have something called as sequence of symbols. Sequence of symbols. So this is sequence of symbols. Say symbols can be your alphabets like A, B, C, D, or anything like that. That will be your information source in terms of digital. Okay. Then comes the next block, which is called as source encoder. So here you are having source encoder. Now, the work of this source encoder is that it will convert the symbol sequence into binary sequence of ones and zeros. That means this symbols will be converted into binary sequence here, binary sequence of ones and zeros, binary sequence of one and zeros, 1 0 0 1 1 0. In that way, you can have a binary sequence. So the source encoder is converting the symbol sequence into binary sequence of zeros and ones. Okay, so here we can also tell that the symbols produced by the information source are given to the source encoder. These symbols cannot be transmitted directly. Therefore, these symbols are converted to digital form, binary sequence of ones and zeros by the source encoder. The group of bits in this will be called as a code word. For each symbol, there will be a unique code word. Say, for example, if the symbol is A, say if it is A, if it is A, then you can say the code word is 1010. If it is B, you can say the code word is 1011. Okay. If it is C, like that, symbols can be converted into your binary sequence. Clear? So that work is done by the source encoder. So now till this process, what all we have done? We have seen the source will be converted into digital, then you'll get symbols, and the symbols will be converted into binary numbers by the source encoder. Then comes the channel encoder here. Channel encoder. Okay. Now this a channel encoder will add some extra binary bits, which are not information, but it will add some extra binary bits, which are called as redundant binary bits, to the input sequence to avoid errors due to noise and interference of the communication channel when the signal is going to travel. Okay, so here you are going to add some more extra binary bits in some sequence which will be known by the transmitter section only. So some more binary sequence or binary numbers are added to the information. So this was your information here. This was your information sequence. Now for that information sequence, some more binary sequence, uh, which will see that it will avoid noise and interference whenever the signal is going to travel in the communication channel. So after adding the extra bits, again this will be a binary sequence only. This will be a binary sequence only. Okay. So you have added some extra bits so that those bits can be used to verify, detect, check, and correct noise and interference when the signal is going to travel in the channel, in the communication channel. Okay. So after that, the binary stream, the complete binary stream with the information plus the channel encoded bits, it is given to a digital modulator here. Digital modulator. Now here it will be like this. Say if your binary sequence is 1010. So it can be represented in any line format. In any line format. Say I represent it like this. This is 1, this is 0, this is 1, this is 0. I represent it like this. Okay. Now this message, this is your information signal in digital format. Okay. Now this message cannot travel alone for long distance communication. Now, this message has to modulate a carrier. So, a carrier will be a high frequency carrier, high frequency or carrier. So, when this message modulates this carrier in terms of amplitude, then whenever you have 1, you will get amplitude. Whenever you have 0, you don't get amplitude. Whenever you have 1, you get amplitude. Whenever you have 0, you don't get amplitude. Something like this will come, and that type of modulation will be called as amplitude shift keying. Amplitude shift keying. Okay. Now, if you vary the frequency for ones and zeros, say for 1, you're having a high frequency, and for 0, if you put a low frequency, 1 high frequency and 0 low frequency, then you're speaking about something called as frequency shifting FSK. If you vary the phase for ones and zeros, then it will be called as PSK, phase shifting. Okay. So these will be your digital modulation techniques, ASK, FSK, and PSK. Now, on the similar concept in your analog communication, you have studied amplitude modulation, frequency modulation, and phase modulation, AM, FM, and PM. Now here AM will be representing like ASK, amplitude shifting. FM will be represented like FSK, frequency shifting, and PM will be represented like PSK, phase shifting, because our information is in terms of digital. It is binary information, and that is going to modulate the carrier, and therefore the concepts of modulation will vary, and these schemes of modulations will be called as amplitude shift keying ASK, frequency shift keying FSK, or phase shift keying PSK. Any one of this scheme you can use and then send your signal on the channel here. Then it will start going on the channel. Now the a channel is nothing but it is the connection between transmitter and receiver. Now here the top line, whatever you have seen from source till modulator, this was your transmitter section. This was your transmitter section. Okay, this complete is your transmitter section. And below what you see, this line is your receiver section. Receiver section. Okay. And in between transmitter and receiver, you are interfaced with something called as electrical communication channel. Okay. It is the connection between transmitter and receiver. It is established through communication channel. The communication can take place either with wire lines or wireless free space or with optical fibers or with some other kinds of cables by which you can do the communication. Okay. So that is your communication channel. Okay. So here you can see a sequence of addition of noise. So here if you want you can show addition of noise. Noise can be added when the signal is traveling through the channel. Okay. So this will be input, this will be plus, this will be plus, so noise will be added, and then it will go to the receiver. In the receiver section, the first thing what will be there will be a demodulator. So here you can see your demodulator, digital demodulator. Okay. Now demodulation. In demodulation, the binary bit stream is recovered from the modulated high frequency carrier. Now, whatever the carrier was modulated, from that you have to recover back the binary sequence what was present here. What was present at the time of after channel encoder, what was present here, that will be recovered back after demodulation. So this you have to get back binary sequence. Okay. Then you have channel decoder. Now, channel decoder will again work exactly opposite to that of channel encoder. So, after channel decoder, you should recover the information bits which were emitted after source encoder. So, this bits should be obtained at this stage. So, it is just going to do the opposite work of this. Then you have source decoder. Then this source decoder is one which will convert the binary output of the channel decoder into symbol sequence. So this will give this symbol sequence back what was there earlier, original. Okay. And then you have your output transducer and output signal, and where the destination part comes, the symbol sequence is further given to the respective destination. Okay. And this destination is one where your electrical signal is converted to its original signal. Say for electrical signal can be converted to sound signal in case of a loudspeaker as an example, and that actual output you can get here. Okay. So this was your functional block diagram of digital communication system. Okay. And this figure shows that block diagram, and the purpose of the system is to transmit messages or sequence of symbols from source to destination point at a high rate and accuracy. Okay. And all these blocks we have explained. Now, turn by turn, we'll see a note on every block. Now, next, the source can be analog signal, example sound signal, or it can be a digital signal also. But if it is an analog signal, then it has to be converted into digital signal. That was our first block. The second block is input transducer, which takes the physical input and converts it to an electrical signal, example microphone. This block also consists an analog to digital converter where a digital signal is needed for further process. A digital signal is generally represented by a binary sequence. That is what we saw after our input or transducer. Then we have source encoder. Now the source encoder compresses the data into minimum number of bits. The process helps in effective utilization of the bandwidth. It removes the redundant or unnecessary extra bits, and you will see that the symbols are converted into proper binary bits after the source encoding. Then you have a channel encoder. A channel encoder does the coding for error correction. Due to the or transmission of the signal, due to the noise in the channel, the signal may get altered, and hence to avoid this, the channel encoder adds some redundant bits, that is extra bits, to the transmitted data. These are the error correcting bits. Then you have digital modulator. The signal to be transmitted is modulated here by a carrier. The signal is also converted into analog form from the digital sequence in order to make it travel through the channel or medium. So here what is going to happen is the information which is in binary form, which is in binary sequence, ones and zeros, okay, digital information, that is going to modulate a high frequency sine wave carrier. It is going to modulate high frequency sine wave carrier. As we have told earlier, if it varies the amplitude of the carrier, then we will get something called as amplitude shift keying, ASK. ASK. If it varies the frequency of the carrier, we'll get frequency shifting, FSK. And if it varies the phase of the carrier only, then we'll get phase shifting, PSK. This will be the basic three types of digital modulation techniques. Okay, so these one of these techniques will be used, and then the signal or then the information, then the data will be sent through the communication channel. Then what is a channel? The channel or a medium allows the analog signal to transmit from the transmitter to the receiver end, as we have seen earlier. Then you have digital demodulator. This is the first step at the receiver end. The received signal is demodulated as well as converted again from analog to digital. The signal gets reconstructed here. Then you have channel decoder. The channel decoder will do the opposite work of channel encoder. So a channel decoder, after detecting the sequence, does some error corrections. The or distortions which might occur during the transmission are corrected by adding some redundant bits. This addition of bits helps in the complete recovery of the original signal. Then you have source decoder. This will work exactly opposite to source encoder. The resultant signal is once again digitized by sampling and quantizing processes so that the pure digital output is obtained without the loss of information. The source decoder will see that it recreates the source output, and it will see that the binary stream which it has got from the channel decoder is converted into sequence of symbols. Then we have output transducer. This is the last block which converts the signal into original physical form, which was the input of the transmitter. So it will get back your original signal. It converts the electrical signal into its physical output. Say, for example, if you're using loudspeaker, electrical signal will be converted into sound signal. Okay. So this is how the last block works. So here we have seen the a transmitter section and receiver section along with a communication channel for a digital communication system. And then the output signal, whatever we get, is produced after the whole process. Example, the sound signal from the loudspeaker can be recovered. Okay. So students, this was the explanation for block diagram of digital communication system. Thank you very much.